use the mirror equation to determine the location and characteristics of the image that's formed here. We'll decide, like, what is the magnification, what's the orientation, is it real or virtual? We'll do all that. We also want to draw a complete ray diagram to solve it, and we want the equations to match our diagram. It says label the principal axis, center of the sphere, focal point, focal distance, image height, and all this stuff. So let's do it. Okay, so first of all, the principal axis is just like it was for lenses. It's this horizontal line that goes through the middle of the spherical mirror. Let's put a 2 centimeter tall object 8 centimeters in front of this mirror. Now that means from the mirror's center. Okay, so I'm going to count over 1, 2, 3, 4, 5, 6, 7, 8. So I want my object right here. It's got to be 2 centimeters tall. Okay, there's the object. All right, if we want to say what the distance is, we can use DO equals 8 centimeters. Now the center of the sphere is going to be here. We label that point with a C, but it is not the focal point of this mirror. And, why not? Like, why don't the rays bounce through that center? Well, if you trace a parallel ray, you'll see why. That ray is headed to the right. If I were to draw a radius for this spherical mirror, then that radius would have a 90-degree angle with the mirror surface. But since it's a mirror, we're dealing with reflection. But the ray is not going to be reflected such that it comes out with a 90-degree angle from that mirror surface. That wouldn't happen. We said before that the angle of incidence would equal the angle of reflection for whenever we're bouncing a ray off a mirror. So what we want to do is we want to draw a ray which comes out from there at the same angle that it came in with. Now, I'm going to have it go through this point here. And that can be the angle of reflection. But I hope it's clear that that's not exactly the right angle. The angle should be a little bit bigger than that. But for the purposes of doing a mirror construction, we want the focal point that they bounce through to be half the distance of the radius. Okay, and that is a good approximation as long as the object is small relative to the radius of the mirror. In this case, the object is not that small compared to the radius of the mirror. And if it was a little bit smaller, we would get like an even better image. Here we'll get some significant aberration, some blurring perhaps of the image. All right, but anyway, we'll do that. We'll have the ray come through the focal point. Now, what's another important ray when it comes to a mirror? Well, not just the parallel ray, but there's also an important ray that hits the very center of the mirror, like that or so. Yeah, see, that ray is going to come in at a certain angle. And by symmetry, it's going to reflect with the same angle. So it ends up crossing through these points here. It's just going to go like this. All right. As you can see, it comes back to the object's location at -2 centimeters, because the object was 2 centimeters high, and that ray is going to come back with -2 centimeters. So that's just an important ray that's like usually helpful to draw. We want to look for the intersection of the rays if one exists. In this case, there is an intersection right here. And that's going to be the location of the image. It's an upside down image. I'm going to draw it solid though, because it is a real image. I say it's real because the rays really do go through that point. So this is a real image. It is inverted. All right, and that's going to be the location of it, DI. All right, so I think we have pretty much drawn everything we need for the construction. It'll have a height for our object, HO. Our image will have a height of HI. And we just want to mathematically find all those. We want to use for this the mirror equation, which is the same as the thin lens equation, but with one addition. All that part is the same. That's just the thin lens equation, right? But we can also put in this other side of it, 2 over r. R stands for the radius of curvature of the spherical mirror. All right. Let's plug in our numbers. I'm going to just ignore the 1 over f part, because I wasn't really given the focal length, I was given the radius. So I'll just use that. I could find the focal length if I want. It's just going to be 2 centimeters, of course. But I don't need it. All right, I'm getting an image distance of 2.67 centimeters. Now we can check our guide here. It says that for mirrors, SO should be inputted as positive if we have a real object in front of the mirror. That's what we had, so we used +8. That makes sense. SI will be positive if the image is real and located on the object's side of the mirror. So that's one thing that's just different. It's different from lenses. See, the guide says that for lenses, SI will be positive when the image is behind the lens and negative when the image is in front of the lens on the same side as the object. So it's just something to be aware of, that for mirrors the convention is different. Note this as well. F and R should be inputted as positive for concave mirrors, but negative for convex mirrors. That is also opposite of lenses, because for lenses, F was positive for convex lenses and negative for concave lenses. So that's just something to look out for. Okay. All right, let's find the magnification though. We can use negative di over do. Now our distance of our image was found to be 2.67, and our distance of our object was originally 8. As you can see, the magnification is going to come out negative, so the formulas, they just work out perfectly for all these situations. Negative 1/3. And it does look like our image is 1/3 of its original size that the object was. All right, lastly, we'll find the height of that image. Same formulas that we used for lenses. The height of our object was 2. So that makes the height of our image negative 2/3. That looks good.